Now we will start the share screen and we'll do it. I hope that everybody can see part of the screen shared. If you see the full screen and the black sides from two sides, from the left and from the right, please turn off the full screen mode. Just press the ruler on the window of the Zoom and ask to exit full screen. This way you will see from the left Zoom shared my screen, and from the right you will see your screen, and you can start MATLAB and we can work together with my MATLAB and your MATLAB. And also some more technical questions. I hope that everybody get already via electronic mail attached file, zip file. It consists several small files, and I hope that you already unzip them and full special, not special, but single folder. And we will open MATLAB, and your MATLAB should be open in this folder where all our files are already placed. And now about this short course, 4 meetings. Today we will work only in MATLAB, and we will learn about modeling and simulation in MATLAB. The second meeting in 2 days, we will speak about Simulink, and I also hope that everybody already has in his MATLAB already installed Simulink as a part, as the main part of MATLAB. The third meeting will be dedicated to building a graphical user interface. We will learn how to use with live editors and how to use application designer to build application in MATLAB more beautiful, more attractive. And the last one, we will maybe discuss some more complicated examples, and we will speak about projects. And let me also tell some words about MATLAB itself. MATLAB, I prepared some files. What is MATLAB? MATLAB could be described as a high-level language which has many special toolboxes for making things easier. It also is a program for not only scientific engineering calculation, but also for analysis of data.
Excuse me, can you please mute everybody? There's a lot of outside interruptions and it's very disrupting.
And also MATLAB is a family of programs that includes basic programs and also a large number of toolboxes. And I tried for today to show you the number of toolboxes that we have in MATLAB, the recent version 2028 in the Technion. And the number of toolboxes is more than 100. I can show the list. The number is so large that if you cannot maybe see the letters, I can read you. There are, for example, aerospace engineering toolbox, audio antenna toolbox, computer, communication, filter, optimization toolbox, signal processing toolbox, Simulink itself, vision toolbox, wavelet toolbox, and all the other. It means that today MATLAB, it become a subjectively oriented program. And if you wish to do something in any subject, in any field, you should know not only the MATLAB itself, but also the toolbox that is built especially for the MATLAB. Maybe I can mute everybody because it's difficult. Let me see if I can do it. More mute all. Okay. Now, what is MATLAB good for? For example, for analysis of dynamics and solving of equation, differential analysis of the signals and system in time domain and in frequency domain. Here we have examples of the solution of the equation and the results as a time plot. Also, we will start tomorrow, date after tomorrow, the Simulink modeling. Simulink is just a device that uses graphic user interface block diagram to build a model. It's very simple. It's kind of, how to say, child constructor to build a system, a large system with small blocks together and connect them. And also Simulink includes, in addition to blocks, it includes very beautiful instruments. And here I put some examples from the Aerospace Toolbox, kind of instrument indicator, and we will use maybe in the last session for the jet plane model. Also, MATLAB is good for analysis of live signal. We can measure, we can acquire data with different sensors. We can save them in our computer. We don't need oscilloscopes. We don't need analyzers. We can, anything we can do today in MATLAB and make this analysis in any domain, in spectrum, and plot these results, plotting very beautiful plots in 2D plots and 3D plots. And last slides about general things is the possibility of MATLAB to be connected to real hardware devices. We can use a special protocol, for example, serial port protocol RS232 to connect to scopes, generators, analyzers, and produce analysis, or maybe to get data, to acquire data, or to put signals to the real object using the MATLAB. Also, MATLAB has a large variety of data acquisition toolbox devices. We can connect analyzers from national instruments, from data translation. There are a lot of firms that can be, which devices can be used with MATLAB. Also, MATLAB is good to connect the image processing devices like camera, web camera, real camera, special card, video processing card. And vehicle network toolbox allow us to work with the interface bus interface devices. And MATLAB can connect not only using the serial port, it also can be used for connection device with the USB port and also with the LAN, with the cable, with the internet, and the Wi-Fi or cable internet connection. And this is why MATLAB today become a large, rich instrument to work, and I think that everybody who needs this analysis, especially real-time analysis, should know MATLAB. And also, let me say that MATLAB today is so huge that it likes to know how to play piano. If you need to play, you should do something several hours, maybe a day, a week, to know how to work. Okay, that's all about MATLAB, and we will start about our examples. Let me close the PowerPoint. Okay. Please open MATLAB command window, and please look that the address line in your command window is pointed to your folder where our files are located. Our files, I mean the attached file that we sent 2 days ago. Okay? Now we can start from the, I will say, important thing to start with the clean screen and clean workspace. We will put the command clear all the variables that can be there. We also close all the window, all the figures that can be maybe open. And also we will clean the command window itself, okay? Now let's start from the first example. The first example is modeling a simple static model of static deflection, of the beam deflection. To see this kind of model, a kind of object, we will use the figure that we send to you. And for this, we will write a command to open this figure. Our figure, let's P, is equal, we will read inside the workspace image read command, and the name of the file, name of the figure file, picture file is beam pause deflection .jpg. If we write this without mistakes and every line we will close with .psych, we know I have a, let me check, beam underscore, no, let me see, beam deflection. JPG, sorry, JPG. Okay, now when the picture is inside the MATLAB, inside the variables, we will open this image, show this variable p.com. Okay, here is our first simplest example. The example is a beam which is under force that is working its work within the any point of along the beam, and we need to calculate the static deformation of the beam. The deflection of this beam is kind of pictures, kind of degree which structure element is displaced under a load due to its deformation. Here for two supports, for two side supports, we have already the equation to calculate this deflection. We have a classical solution, already closed solution. This is why we also send to you this solution, and we can already also insert the solution inside the workspace. Let's do it. We prepared a special file. The name of the file R1_1. We load this file. Inside this file, there are two strings, let me say. The first one is Y1. You can open it. It's a string. You see that the string is close with the quotes, with the apostrophes. It means that just a text. It's not an equation in the meaning of possible to execute the equation. It's just a string. And we will see how to convert, how to use the string as an equation in MATLAB. Also, this classical problem of the beam with two supports, it has two equations, because the first one is for the left side of the point of our load, and the second equation is through about the right side of the beam. Also, we have this right side. It's another equation, Y2. Also, it is a string, just a string. We can see how we can use. In this equation, we have different variables. W is a variable, it's our load. B is a length of the beam, all the lengths minus A, where the coordinate of the force. And also we have E, it's a model Young, or modulus of elasticity. And also we have I is area moment of inertia. And B we already know. X position, it's just our position of our beam. That's all. Now let's try to insert the variables. We will use a special maybe way to use a command input. There is a very useful, let me show you. For example, we need to know about the length. So we should write L is equal to input. We close this input, use the apostrophes. Inside we can use any string, and let us put this, for example, insert beam length. Length is equal, and when we press enter, we will see this question, and we should answer this question with a number. Let's do it. I press the, yeah.
Please ask the students if all of them have their MATLAB open, or do they have problems with opening it?
Okay, let us try to ask people. Please let me see your faces, and I can unmute everybody. They are unmute now. Please, is anybody has a problem with its MATLAB?
No. No, it works.
No, everything is okay.
Okay, we can just leave your unmute, sorry, but please do not make some noise because it's difficult for others. Okay, now again we will share the portion of our screen. Okay, now when I press enter, we can insert the beam length. Let's say it could be 10 meters, for example. Okay, and now we have this L is equal 10. Now we should all other parameters. Let's put the coordinate of our force. A is equal, again, input. And let's, in quote, insert the coordinate. Reload. .seek, enter, and now we have this question we can answer. Let's say for the left side, it could be 1 meter, okay? In the question next, we will do it maybe quickly. The load itself that is input, and the load, I will just put the load value. And it could be a large value, for example, Newton. Okay, we should also enter, but let's do it in a more quickly way. A modulus of elasticity is equal to 200. It's a real for steel, for example, multiplied by 10 in power 9. It's our elasticity, and is because we have meters, the inertia, moment of inertia could be small. For meters, it could be 1,001. Okay. Now, we already have all variables, so we can start the calculation. We should calculate the beam. B, it's a part of length minus A. It's the first what we need to do. And also we need to calculate the position in the meaning of different points of our, let's choose number of points along the length. Let's take, for example, 50 points. And we just put the X is a line space function from the 0 to A. The 0 is a minimum value of our X. The L is the maximum our length. And the number of the points, let's say 50. Okay, now we can just estimate the position of the deflection is equal to our X before the coordinate of the load. It means that x, but less or equal of a. Sorry, less or equal of a. It's our position now. And let's now calculate the deflection from the left side of the beam. We can do it y as the argument of only for this position from the left is equal. Now we should translate the string to the real equation. We can use the command evaluation, eval of our string. The string is y1, we already saw it. This way we calculate the position. Now let's do it for the right side of the beam. This is our new position. New position from the right side is equal to the x, but now x is more large than a. Again, we will use the second equation. Y for position is equal to evaluate. Now our second equation. Where is our, let me see.
You wrote down PS when you meant to write post.
Oh, position, sorry, position. Right, thank you. Position, and that's practically all for our calculation. Now let's try to present the result as a graph, for example. We will use this graph of the deflection each 50 points as a stem, program stem. Let me show you how it will be. The x is our coordinate. There are 50 points in x and also 50 points in y. And we will use, for example, straight line, and color will be blue, and maybe we don't need marker as a circle there. We will use marker size, or marker just 0 or none, sorry. Okay, let's see what we have now. Here's our graph of this deflection. Let me show you. Okay. Together with this graph, we can also plot the deflection of the beam as a beam. Let's do it. First, we will put, we'll hold on this our graph of the deflection, and also we will plot the deflection now as a line. Plot x, y, and doing as a, for example, not line, like a dash line with the color, black color, and maybe line width, maybe more thick line width. Okay, now we will have together, but it's not looks like a beam because there is no thickness of this. We can plot the same plot, but now just make a small step with the y to plot the thickness of the beam. Let's do it like this way. Multiply by maximum of the deflection. Okay, it looks like a beam now, at least. And we also can build here the beam itself before the deflection, before the force. We will use, for example, a rectangular function, and we will use this way. The width of the rectangular can be our length width is equal to our length. Also the height.
Some of us got a straight line and not the same graph that you got.
Sorry?
Some of us got a straight line and not the figure that you got.
Another figure we cannot see. Have you used the hold on, also the stem picture and also the graph?
Yes.
No, not about the hold down. Before the hold down, we didn't get the blue lines. We get all the blue lines at the 0 point. So we get the result that the beam is not deflected.
זה לא כזה קשה לצייר, כאילו, פאקינג צירף במטלב ולעקוב חברות. סתם, שלא מבין מה קרה לך.
It should be. Everybody has a problem, has this kind of error, or only two of you?
For me, it works fine. I think I got the same problem.
Speaking the truth, I cannot understand the problem because we can just, I can show you all again. Let's check every line here, or we'll do it this way. We just, let me finish, and we will put all this comment in the editor as a script, and we will check where is the problem, okay? Let's finish this plot. And now we should make this rectangular. It's also maximum of the y. Okay, now we have a rectangular. And position. It starts from 0, also the width 0. Now we have width. And we have the height. And also as a variable, and we can maybe use a line width also.
Michael?
Yeah.
Sorry, I can't see what you are writing.
Sorry?
I can't see what you are typing now. Like, could you please move up the workspace?
I didn't catch you because the sound is not so good.
מיכאל, אם אתה יכול להרים טיפה את החלון של המטלב, כי הסרגל של הזום מסתיר אותו קצת, בדיוק, זהו.
Okay, now we're...
עכשיו טוב.
עכשיו טוב, wonderful. Okay, and also we will make the, maybe the, for the face color, we also black. Let's take the black color, face color, sorry. Okay, now I think it looks like we will get the rectangle. Let me see. No, rectangular position. All right, it should be close in the, no, rectangular position. Okay, this is what I tried to do, just the beam itself before the deflection and the deflection. And the last thing we can just play, we can put here also the arrow as a force. For this, we can use a command, MATLAB command QWIR. Let me show you how it could be. It starts from the 8. A, it's our coordinate of the force. And also it has 0 as a thickness there, and also the number of the volume of the value of the force. Our force, and multiply by maximum of the deflection. And we can divide it by 2 because it's too much. And the color, let's check the, choose the color of the arrow. It could be red. Maybe the line width also. line width, line maybe 5 more, and also the color of the the size of the arrow itself. It has this feature, max head size, and it could be maximum is 1, but we choose a little bit less. Sorry. Okay, it looks like we finished. Let me check. Again, queer. Oh, here we can see now what I will try to plot. The beam itself before deformation, the deformed beam, and the arrow shows our load. Now, about let me copy everything that we have in our comment window, copy these lines, all these lines, Control C, and we open a new script in Matlab. We will open an editor. In editor, we can paste all this line, and let just remove everything that we don't need, all mine errors, and we'll leave only what we do need. This is just for information. Okay, insert.
גם שורה 2.
Okay, now let us see what we can just throw out from here on its position. Position, stem, it's okay, rectangular. The first one is rectangular, okay. I hope that this, all this modeling is these 25 lines. Let's just save this file as
יש למעלה עוד דברים שצריך. With line 10 and line...
Let me check. Line 10, it's our modulus. It's, we don't...
9.
We don't need it. Okay, position, plot. Okay, that I believe that there is a program. Leor, it's you that who helped me.
7 and 5 also.
7, let me insert the, yeah. Okay. Right. Okay, now let's save this file as an M file, save as. We'll make the name for the first model R1_1 M file, okay? Now we can just run this file and evaluate everything. Let's see if it works. I run the file and we have the first question, we have the length of the beam, we put again 10, sorry. The coordinate, let's take 9 for the right side, and the load, it could be the same value, enter. What we have as a plot, let me see. Yeah, here our plot, a new one plot. We have forgotten the axis. We can just limit the axis, but it's not so important. Okay, this is our model. Also, I will show you, maybe it's interesting, we also can make a result of our calculation of our modeling as a good-looking table. For this, we can use a command in MATLAB fprintf. This command also can produce a table in the workspace. It also can make a file, write a file as a special table. Let's do it. For example, f print f. We have for the first row we can write our name of our model, for example, length, and also the second could be for example, here we can put is equal the name itself, number to string. This is our L, and new line in quotes, and also the load position. Also and is equal, and also number to string. Okay, I believe that that is enough. Okay. And for this, because we use a string, we should use a bracket, a square bracket. And close them. No, number to string num to string num. Length.
You have something wrong with brackets.
But let me see the close.
After the num to string, after the first num to string, you close it twice. So just delete one.
Okay. And then the second one.
Yeah, here exactly, just delete this one. No. On the left side, where you wrote num to string, and then in bracket 1.
Yeah.
You have 2 brackets exactly.
Okay, maybe now it's okay. Yeah, here we can see, we can continue with all the parameters, but we can get this table, the length of the beam and the load position. We also can continue the maximum of the deflection and so on. Okay, I think that this is the simplest example of the model of static deflection when we have already the equation itself, we know them, and just we use it as a formula. Now let's go to the solve some problem of dynamics problem of in the Matlab using the solution of the differential equations. Again, to do it, we can clean our workspace, and also we close everything, all the figures, and clean the command window. Now we can start. We don't need the command. Okay, and we will start again with the problem. Let me show you the problem again. We've already prepared this graph, and also the picture is equal image read, and we have already picture as a ODE 1.jpg file, graphic file, and we can insert it in the Matlab. Now we can show this graph. Okay. In general, we will start from the first order of differential equation. It is looks like the first derivative, dx over dt, is a function of x itself and t. And the problem is to solve the equation using integration. We should find the x as integral of our function fx, and use for this MATLAB function OD45. Let's do it.
Michael, you have a new message.
This is for this we will use the equation, solving equation in MATLAB as an example. Here we have the example. The first derivatives as a quality example: 3 multiply exponent in minus t with initial condition x0 equal to 0. For this, we should first to write this equation in MATLAB as a separate function. Let's do it. We will open a new script, and a new script will write this example. I will put it down to see the equation itself, and also to see the MATLAB editor. How we can do it? We just write that this is a function. In function, we should define the first derivative, dx dt by dt, and we should choose the name of our function. Let be RH1, right-hand side 1. As a input, we use t, and x is our input. And oh, sorry, I use not in editors, my fault. Where is my editor? Here, the editor. Again, we will put it in the editor. We put this again, function dx over dt is equal to the name of our file, of our function file. Let's say 1, and from the right side is the input, and the second line is the equation itself. Let's see, it's absolutely the same as it is written in the picture. Dx over dt is equal to 3 multiplied by exponent minus t. Okay, and the end of our function. Let's remember, let's save our file as a special MATLAB file, as a function file. Save. MATLAB is clever enough. It understood that we use RHS1, and you already know that that is our function name. Okay, we just put it. And now we can use the workspace to continue to modeling our result. To start with the modeling, we need the initial condition. The initial condition, and also we should just insert the time. Let's say we need time from the 0 in increment time 1,000th seconds, and for the, let's say, 5 seconds. And also we will need to insert the initial condition of our x. X initial is equal also, let's say, 0. Okay, now we can use the MATLAB files, MATLAB command OD45 to solve this equation. From the left, we put the solution already. This is our output of our function, the output t, and our solution that we, till now, we don't know, but we do know the function itself. We use the command ODE45. And we just call our function that we wrote our right-hand side 1. And for this function, we have the initial time. We have the initial condition of our x. Okay, let's start. Let's press enter. We start this solution.
Michael, someone raised his hand.
Okay.
Michael, I just want to say something before. I think the T array is wrong. You miss a column there between the...
Right. Let us...
Modify.
Right. Okay, again, we will... But if raise a hand, let me stop the sharing to see these... participants. Is there any questions, please? No, it looks like everybody is or sleeping or maybe listening very attentively.
אם אתה לוחץ על משתתפים למטה, participants, אתה יכול לראות מי מרים את היד.
But I already pressed, but I have no, I cannot see the
excuse me, sir.
It's you, Elio, only you.
Yes, probably.
But
okay.
Thank you. Yeah, you already helped, and please continue to help. Okay, let's again. We will go.
So, excuse me, sir. Sorry to disturb you. Would you please tell us again how to input or say the save the function to the files? Like it seems that it is my function still not works in my command window. The RHS one. I don't know how to save it to the files. Would you please?
Okay. Let's do it again. We
Thank
will
you.
Continue to our shared screen. There is our picture. Let's make it smaller. Okay, let me clean the workspace. In the workspace, we don't need nothing because our function we should write in the editor. We will first open new script. It opens an editor. You see,
Michael, you have a new message.
A different window. That we have two windows now. There is down. We have a MATLAB window. It's MATLAB workspace window. Command window, and upper we have an editor. It's an editor of MATLAB. Inside the editor, we already wrote the function. Let me show you, because here is our function. It consists only 3 lines. Function is just for MATLAB to understand that we should use it as a function. We have output of the function as a first derivative. The name of our function is right-hand side 1, and this is the input. We insert the derivatives, and in round brackets we have the output of this function, time, and our solution x. Now we should define what is the first derivative. Let me show you again. Our first derivative is just 3 multiplied exponent. We should just write it, we should do it inside the function. And we did it. First derivative is equal 3 multiplied by exponent. And at the end, we should close this function. Now, when it is all written in the editor, we can save this file as separate file in MATLAB. We should press save, and we can choose any name, but we should use the same name as we use for function, because MATLAB should call this function. To know what the function should be called, it should be this name. Okay, now we ask MATLAB to save as right-hand side 1.m file. We already have it. Do you want to replace? Yes, I want to replace it. Now we have this function. This function is inside the MATLAB, and MATLAB knows how to call it. When we don't need editor anymore, we just can close the editor, and in MATLAB itself, we can just call this function. How we do it? We just call the procedure ODE 45. We call our function RHS1 with the initial condition t and x0, and we should get, when we press enter, we should get the solution. Now the small question we should represent, we should plot the solution. It's very simple. We just can plot it, our solution x as a function of time, and we can do it. I prefer to do it with the thick line because it's very, we can see it from the far line width, but it's just my caprice. Okay. We also can make reading in the line. Okay, here we have our result, the solution. The x will change exponentially from 0 time to 5 seconds. Looks like this. We can change the time, we can change the initial x value and get the result, how the x will evaluate during the time for known first derivative of this x. Okay, can I continue with the next example?
Yes.
Okay.
Yes.
Okay, let's do it. The next example will be the second order of the differential equation. Also, we already prepared for you this example. Let's close everything. And we will start. Start our picture again. Picture is read, image read, and the file name is ODE a.jpg. Okay, now we can show this. Okay, here's our equation. Now it's a second order equation, differential equation. We should find x. We only have the first derivative, the second derivative, the first derivatives, and the right-hand side is a sine signal, sine function. And what we don't know nothing, we don't know anything from the x. We should find the x. What we should do, let's write separated code file as a function. Again, we'll start, I will do it slowly. We will start new script. Is in the new script, I mean the editor. And we will put it together with our equation. In the editor, we start the same way. We should point that this is a function, and we should find the input of our function. It's the derivative. No, there is a very important thing before we'll continue. MATLAB, this command ODE 45 can work only with first order equation. this means that we should convert our equation for two first order equation. Our equation can be any order. Now we have second order, but we first should convert it. Let me show first, sorry, before the editor, let's see how to do it in this conversion. It could be maybe a separate figure. Let me show you as a separate figure. This is the first figure. Let's open in the second figure. Second figure, and we will put inside, whoops, inside our Zoom. And we also prepared, it's also image read. The name of the file is 2 underscore first, 2 first order powers order dot jpg. And now let's show this conversion image show. Okay. Oh no, it's to first. It should be
You didn't call to the imread. You didn't put it in P. So
this is why. Okay, let's check.
Try it in show and then answer.
Yeah, this is one another. Now we will show this one, a new picture. Now let's see how it works. We can do it maybe more. Okay, we just should insert new variables. We will choose the first x1 is a new variables is equal to our old x. Our next new variables x2 is the first derivative of the x. Here's our just substitution for two new variables. Now let's take derivatives of these two variables. We will have that our new variables, the first derivatives x, the first derivatives of the old one, but the second x2 now is our old second derivative. This way, we will have two new variables, but each one will use only first derivatives. And we do this replacement. Now, we will have our new variables is the first derivative x2, and the derivatives of x2 is our equation. Here we'll get a new equation, two new equation, first order two new equation, instead of our initial equation with the second order. I believe it's clear how we can go from second order equation to two equation first order. Okay? When we have this substitution and this replacement, it's very simple to write the function to solve this, this ordinary differential equation. Again, in MATLAB, we will start our editor, and we will continue in the editor that our dx dt, but now it's a function of two variables. We should remember is again, let's choose the name of the function, right hand side could be, and the initial, again, it's the time and the x, but again, every x and the first derivative is x. Now there are function of two variables. It's a vector today. Not today, but just for our example. And let's calculate the first derivative of it's now dx dt. Dx dt is first column. It is equal to x dot pseq. Now we will use.
זה לא צריך להיות,
Sorry.
זה לא צריך להיות בסוגריים, dx dt בסוגריים אחד, כדי לשים את זה בעמודה?
It could be, yeah, it could be, we can write it as a matrix, but maybe for the beginning, let's do it just as a line. Yes, it could be right as a matrix, but it also can be right separately, each line. And this is the second line. It can be, is this way, 5 multiply x. Let's see, the second plus, how we will, there was 4, yeah. There was 4 multiply x, the first, and our sign. And sign was 10 multiply t, if I, yeah, t multiply t. Okay, dot pseq. Now we will shoot. Now we will put it as a matrix. We will put two variables together. We can do it just for the beginning, but I prefer just separately. Is equal to the first one and the second row, dx dt2. Okay, it looks like, okay, no, something is wrong here. No, it's okay, and end of the function. We should save now this file, this special file, special function, we should save separately and make the same name as we choose in the function. Here we choose RHS, we should save it as RHS. Let's do it, save as. We already has it, but we'll just replace it. Okay, we don't need it, and we can now just call this function to solve. But before calling the function, we should choose just insert the initial condition. The initial condition for time will start again from maybe less than 3 seconds. And also we need the initial position for displacement, 0 is also 0. And we will start for the initial, now we should for the derivative dt, it also could be 0. Let's see if everything okay. We can just call the equation. Again, our output time and x, what we don't know, we should find it, is equal to ODE 45, this solver, MATLAB solver, and we just call our RHS function. Oops. Call our function, and the function includes t and includes the matrix R as x 0 and dx dt 0. Let's say, let's check if it's okay. Let's start. It looks like okay. Let's see how it looks as a plot. Now we can plot this result again. Plot tx. We have already tx, t as x as a function of t. Line width we can leave it. We have here, we can just maybe insert some labels. For example, x label, it's our time. Oops. Time.
אתה יכול להרים את ה-command window עוד פעם? שנראה מה כתוב למטה?
With my pleasure.
תודה רבה.
How strange, because I can see the frame of the zoom. It's much more far from the, okay, but it's a problem of zoom. Now let's make the label for y label, and y label could be X, this is our solution, our output. Okay, let's enough. Maybe title. Title could be our equation, but instead of equation, I just write this function of t, Okay, let's start how it looks. Show graph. No, something is wrong here. Line width, we should put the number. Oh, here we have why. Okay, this is why we have no, anybody knows why we have two lines here. Have you any ideas?
Because X was a matrix with two lines.
Right, two variables, because here the x1 is the solution itself as x, and the second row is the first derivative of x, is the velocity of the x. We can show you, I can show you when we put the plot x, here we can just use only one of them. Let's say the first row is the x, the solution, the, let's say, displacement of our equation. And if we choose the second one, we will get only the second solution, the second row as a derivative. It looks like a sine wave, because we have here as a right-hand side, we have a sine. Okay, I hope that that it's enough for the example of the differential equation. And if there is no question, let's go to another example. Is it okay?
Yes.
Okay. But now let us do it much quickly, maybe, because I already sent to you this example R1313A, and we can do it much quickly by using the editor and open the examples in the editor, and we will just execute several lines to understand how it works. Why I sent to you several examples, because I believe that you have time to work with this example, not only during this lesson, but also yourself as a homework, and to have a practice, because only this way anybody can learn and study MATLAB as it should be. Okay, let's clean everything and clear and close and go to our editor. Maybe we can try to put them together. Let me see if we can do it. We will open editor. Open. And we already have, for example, R13 is the next example. Let's open in the editor this example. Let's put it this way together with the command window. The editor now is from the right and the command window is from the left. I believe that you can have the editor docked inside the MATLAB but I prefer to work separately. Okay, now we have two windows again, the command window in MATLAB and the editor. We did it because we need to run separately every function separately. And let's start again from the problem itself. We can just run this section, because here is separation of the section. Please press in the editor the button run section or run and advance. And we should see the picture. Where is our picture? There is no picture. Why there is no picture? Let me see. Because pause maybe, no. Okay, there is our, again, we can run separate lines in the MATLAB, but we can do it several different ways. We can run and advance the section. We can run this section where we have pointed our mouse. Also, we can select one or several lines as I did here and press F9 in your computer. This way you can run only this selection, okay? Now we have the model of the second order differential equation, and we should find the motion of this problem, of this model. Okay. Again, we can write a separate equation to solve the equation. Here, we will write to show you how it looks as in the editor, and I press F9, and here our function that should be written in the editor. We already know how to put these two variables. We did it before, and this is just to repeat it. Let's do it in the editor. I copy this function, copy. I open the editor. I open the new script in the editor. I put this function in the editor, and I only need to save this separate function as the name RHS3, because this is what we choose for our function. Let's do it. We will save as RHS3 in the MATLAB. Okay, now we don't need the editor. We are ready to solve the equation itself. And we should have the editor, because in the editor we have the example. Okay, in the editor we can continue. We should define the initial condition. Let's do it this way, where we should define it and run this section. Okay, we have here the start point, the end point, and the time span. We have the time as from the very beginning, from the start, with the increment 1/1000th up to the end. Now we should define the K and the M. K is the stiffness of our model, mass, stiffness, force, and C is a damping. Now we should find how we can do it. Again, let me select this line and press or run section, or we can press F9. This way I run these values. I insert the value of stiffness and the mass. Also, we can estimate the critical damping. And let's insert the initial position and initial speed and make them as a matrix. And here we can see how to run the equation, but instead of this, we just can do it. Let first, again, for the single time, we can just do this way. Our output, let me show you again, because it's too. Again, our output of the solution is T and X. Again, we call the OD45. We have our file already separately written, and we have the initial condition, and this way we can solve the equation. But let's do it in more complicated way. Let's do it in a cycle for different kind of damping. Let's see how we can do it. For C damping, that is started from 0 up to critical value, we will start several times of our equation, when starting this equation, we will plot each time, we will plot the solution, and we will plot in title, we will plot the number, the values of mass, stiffness, and damping, and we will see that damping each time will be different, and we will use it slowly with the pause of less than 1/10 of the second, just to see slowly as it works. Let's start it. We just should, or maybe run this section. Let's see if it works with this section. No, this section doesn't work. Let us start this way and pause here. Oh, okay, we can see in the title. In the title, we can see that each time the damping is different. For each damping, we plot this solution. Okay, now this is the equation. Let me see what we have here as an example. As an example, we can choose different kind of F. In our equation, we use the force as a function, and we have a special function. In this example, we use a sine wave. We can use example of different, let us do it. Let's open in our editor the function force. I believe that we can do it here in this file. We will just comment the sine wave, and we will open the impulse. What it means, if t is small, less than half of the second, we will have force. Else, for any other time, we will no force at all. We have no force, and this is zero. This kind of excitation is impulse. Let's see how this will work. Again, we will run all the script from the very beginning, and we will press button. You see, now it's not a sine. What is the difference between the sine and the impulse? With the impulse, we have zero at the end of the time. And with sine wave, we always, in any kind of damping, we will have a solution as a sine wave. And here, not, we have a just steady state solution as a zero. Again, you can play with any other kind. Let's do it as a ramp. Again, we will comment the impulse, and we will start the ramp excitation. You see, in this example, our force is running during the time. And let's see what will be with the solution of the equation of the model when the force changes in time. Again, we will run this equation. Just press the pause. There is a pause inside. And here's the solution of the equation for different damping, but when the force is a ramp, just increasing in time. Okay, now we have several more examples, and now we have an hour and a half in our lecture. Do you have how to say force to continue, or what? Let me stop sharing and ask the audience. How many people we have? We have 44. No. What do you think? We will continue with this next examples. Please give your suggestions. Yes, I have that somebody already is agree. Okay, let's do it one more, and let's see what we can do other. Share. Again, we will clean the workspace. We close everything. Clean also the command window. And again, because it works much faster than to write each line, and with my mistakes, it's take a lot of time. We just open already in the editor. Let's open in the editor, new script, and let us open next example is we already R13A. Okay. Editor. Again, we will try to put them one next to the other. Okay, here we have the model as a picture. Let's write again. I just select this line and press 9, F9 in the computer, and we can see again, this is our model, the second order equation. And also we can see the new way of solving equation as a state space model. Let me show this graph. Okay, it's maybe too big. This way we already know how to use it, because this is all our previous examples was written the same way. But now let me show you another way of solving equation and inserting the initial condition using the state space state space equation. Here's our theory. Okay. In this way, in steady space form, is a special form to organize this ordinary differential equation in such a way that it works with 4 different matrices. And each matrix is relevant to our system properties. It's the same mathematical model of our system, and it includes the input, the output, and the system. It's a good way, especially for those who work in control theory, because they usually use this state space form of solution of the differential equation. And also in mechanical engineering, also this form of writing equation is also very, very useful. Now, the first part, the solution, no, let's start from the matrix A. Matrix A in here is this way of matrix. This matrix A, it's called state vector. State vector include the parameters of our differential equation. This matrix also sometimes includes not only the damping, it also includes all the parameters of the differential equation. Now the output of the solution is Y. Output of the solution. It's also matrix, and the output vector includes the solution. In our case, for the second order equation, it includes the solution itself and the first derivatives of the solution. It's output. And what we have here, it's also, there is matrix B. Matrix B here is our input. Here's our matrix B. Matrix B, it's our force. If we, in our equation, force is the right-hand side of our equation, and the in this form of state space form, it's just the matrix of the right-hand side. And let's see how this can be used for solving the same equation, second ordinary equation, but now in the state space form. Let's go back to our editor. And before we can continue, we should just insert the numerical value for everything, for stiffness, for damping, for mass. Let's do it. I select this line and press F9. Now we have in our command window, we have these numbers, and the matrix of A looks this way. If I didn't select the dot space, we can see the A as a state space matrix itself. Let's do it F9. Here our matrix for the value of our parameters. The same way we can just insert the matrix B, C, and let me say that in majority cases in mechanical engineering, this special matrix D is always is 0. Okay, now we have our equation written in the state space form, and now it's very simple just to solve this equation. Let me show how it looks. I will clean the command window, and we will put the system in the state space form. This is just the written form of our system. And let's see how it looks. It looks like 4 matrices. If I just ask what is our variable sys, we will get these matrices. A as matrices of the system state, B as a matrix of the input, the C is the output matrix, and D is always 0 in our case. Now MATLAB allows us to solve this equation very simple, just in one line. When we already have the model written as a state space form, just what we need, we just can write command as any kind of excitation. For example, step excitation. Let's do it. Step as our system, and we can plot it already. We'll plot it itself and show graph. System, sorry. And here our solution of our system. You see, when we use this state space form of the equation, we have a very convenient way of solving. Step is just our step, and we have the solution of the system. We can make any other solution, for example, impulse, solution of the impulse to the system. The same system and the same grid, show graph. Oops. What is the difference? Now our solution is just oscillate over the 0 value, and not the step solution to this constant value, just around the 0. What is interesting that these examples also can allow us also to get the continuous time transfer function, to convert our mechanical system to the transfer function. Let's do it. For example, when we insert the frequency range, first let me show you the transfer function of our system. Transfer function of our system. Here we can see in MATLAB window, this is example of this equation as a transfer function. It's very convenient for those who work with control toolbox and to solve the problem in control theory. And the last thing, let me show how the same system can be converted to the continuous time transfer function. For this, we will use transfer function by using frequency value. F is equal to, again, length space from 0 frequency up to 10 Hertz. And let's take 20 points in this. And our system we will call by using the command FRD, which mean transfer function, and we should use our system and our frequency. And we can plot the results. Plot already, we have our frequency response. And it should be as a frequency. And the frequency response is a complex function, but we will use only absolute value of this function. Again, frequency, this function system, and dot response. And for all frequencies, okay, dot seek show graph. Okay, here we plot the graph of our frequency response function as a second order differential equation of the mass spring system. For those who study vibration analysis, immediately can understand all the behavior of this system, because this is the static stiffness, this is the resonance frequency, and this is the reaction of our response function for the frequencies input much higher than the resonance frequency.